Good morning, all. I'm sure now you are much more motivated and ready to learn more. And as I discussed in the today's class also, that if you keep on practicing along with this, whatever way we are going, by the end of this month itself, all of your programming weaknesses will be over. And if you continue working hard regularly and continuously, by the end of this semester, you will be one of the best programmers and you will be very confident and you will start enjoying programming. So, having said that, I'm sure yesterday we have discussed the polynomial addition and exponent-based issues we have already discussed. So, I'm sure you have done that. And the modularity, etc., I have already demonstrated in the corresponding lecture video yesterday itself. And those who have any doubts, they can see yesterday's videos once again. Today we continue and discuss something more with another new data structure. And all of you have already used matrices in many ways. Mathematics, you have studied matrix in a big way, and you have done a lot of operations. So you know that there is a matrix, normally we say of order of rows into columns, M into N, R into C, whatever you say. So these many elements are normally there. And you have already done lots of matrix operations. Definitely you have done transpose, etc. You have done matrix addition. You have done matrix multiplication, etc., etc. We are going to just look upon those aspects in a different manner now. I say, let's say if I have a matrix of order 4 into 5, so effectively 4 into 5 means I have correspondingly 4 rows and 5 columns. And because we are storing in C programming, etc., so every time we know that their default numbering is 0 onwards. So for this effectively means there are 4 rows 0 to 3 and 5 columns mean 0 to 4. And we have certain values and will be operated on that. Let's assume now this matrix is something like this. So this matrix has certain values as zeros and certain values as non-zeros. Say here I have -3. This. Now, having said, say this is my matrix. In this, if you see carefully, I have, so I'm just focusing so that it remains good. So in this, if you see, probably we have 1, 2, 3, 4, 5, 6 non-zero values. And total values actually were 4 into 5, 20. So out of 20 values, well, nothing significant, not much of a problem. Still, I can say nothing big about this. But imagine I have a matrix of order, say 4,000 into 5,000. And out of this matrix, only, let's say, 300 values are non-zero. And when I'm saying a matrix of this order, it is not uncommon in civil and engineering, civil and mechanical engineering. People study the concept of FEM, finite element methods, and they operate on very big matrices, out of which many values are zero and a few values are non-zero. So I say, if I have only 300 non-zero values, let's say out of this, or maybe let's say 400 non-zero values out of 4,000 into 5,000, most of the values are zero. In that case, I can see that if I traditionally store my matrix, traditional storage, you have already discussed, you have done last semester, a 2D array. 2D array storage will mean 400,000 into 5,000. That means effectively 4 into 5, 20. So these many values, 1000. So we have 10,000 lakh. Almost I am going to have 2 crore values. Out of this, we have only 300 non-integers, non-zero values. These many values will be there. And if I say I am storing with the traditional storage, I need to store 2 into 10 raised to 7 integers. Yes, that will take some space, obviously, because I have values. Now I say, if I am interested mainly, let's say, into transpose or addition or similar operations, in all these cases, effectively non-zero values will be meaningful and other values will have effectively minimum role to play, especially in the transpose. Zeros, if I am not interested to do, or in FEM, etc., zero-based multiplication, or etc., they don't play a role. So most of the time in real applications, my non-zero values will be much more useful. And I say all of their operations where transpose or addition, non-zero values are needed. And I can probably think of a better solution or better storage where I can avoid storing zeros. So how can I avoid storing zero values unnecessarily? And because zeros are too many, so out of 2 into 10 raised to 7, maybe 1 crore 99 lakh and something are non-zero, zero values, and I should unnecessarily need not waste my memory. Now, how to do that? Means that I will aim to store primarily non-zero values. Of course, that helps in improving the storage, as well as it will help in improving the operations. Faster operations will be possible. That we will talk after a few minutes. But I say in this case, I'm interested to store primarily, let's say, value 3, 4, 5, 6, -3, -4. These are 6 values. So maybe I can think of having an array, 1D array, and the store 3, 4, 5, -3, and -4, and then I can think of doing some logic. But of course, you can easily see this is not sufficient. Why it is not sufficient? I lost some useful information. Only non-zero values stored is not sufficient because their properties I have lost. 3 I have stored, but whether 3 was stored at index 03 or it was stored at index 523 or any other index, I have no idea. So obviously, I have forgotten their position. Position means it's a row number and it's a column number I have lost. So I say, still I can now think, I can smell a better solution that when I want to store 3, I can say it is at index row 0, column 3, this is column 3. So row 0, column 3 and value 4, this is one non-zero entry. Second non-zero entry is a 4. I will say it is row 1, column 1 and value 5. So in general, I can say for every non-zero entry, what I need is the corresponding row number, column value, column number, and corresponding value. These 3 values, I'll say this 3 triplet needed. So effectively, I say I need value 0, 3, and 4 as one value. Then I need 1, 1, 5. Then I have one, so this was 0, 3 as 3 value. Sorry, let me correct that. This was 0, 3 with 3, 1, 1 with 4, and so on. 0, 3, add was this value, 1, 1 as 4, 1, 2 as 5, then I have 1, 4 as 6. So I can easily see this is this value, this is this value, this value, and so and so. And then I have minus 3. So this is row number 3, column number 1, value minus 3, row number 3, column number 3, and value minus 4. Now, I want all these values to be stored. So probably I can see that I need something like this. Now, from here, you can easily see that this storage effectively requires 3 int values per entry. One for its row number, one for column number, and one for the value. So for every non-zero entry, I have 3 total integers to be stored. So if I had 400 non-zero entries, that will mean 3 into 400, 1200 integers to be stored. And earlier, for my traditional storage, I said it required 2 into 10 raised to 7 integers. So I can save a lot of space. So this becomes a new kind of a data structure. And whenever I have a matrix like this, such matrix is called as a sparse matrix. So if most of the entries are 0 in a matrix, then we call that a matrix as a sparse matrix. Now that most will be probably defined in some sense, maybe I say 80%, 70%, 90%, 50, 67%, whatever, but most definitely means much more than 50, 60%. So if I have most of the entries 0, then such a matrix is called as a sparse matrix. And this is our another new data structure which we are going to focus today. So of course, this sparse matrix also can be discussed to be called as a new ADT. And for more details, what is this ADT, how it will be stored or represented, and operations, what will be its visibility interface. So I will again suggest you to read a book. I have already discussed in the class today also that at least you should target to read weekly all topics from the book. And the book of Horowitz and Sani is the best book. So weekly, all topics from the book should be read. So if you want to be good student, if you want to learn everything, book will definitely have much more meaningful discussions and depthful orientation of the topics, which we are probably not able to talk in detail in the class. So your target should be programming and implementation daily or after every lecture minimum, at least after every lecture. And book reading, at least all topics weekly. Whatever topics we discussed in 1 week in the class, all those topics covered in the class should be read from the book, maybe relevant pages, at least those many pages. And you should read it from the book. That will help you in maintaining your continuity and covering everything. So sparse matrix is now what we are targeting. So I said sparse matrix storage, we have already discussed that effectively I want this to be an array of certain triplets. And a triplet, I have already said, had 3 values: row, column, and val. Obviously, now I can say that this can be taken as a structure, and what you require is array of structures. So you can definitely do type def, say sparse term, and within that you can store row, column, and val as its members. And then, of course, you can have array of this. So this is optional. You may or may not put, but once you have declared it as an array type def, so now this data type is available and you can declare, let's say, original matrix I'm naming is original, and later I will generate its a transpose. So I generate another transpose matrix of this size. 50 size, I am assuming. So effectively, I have one array of structures taken. Then I say, if I store like this, I have almost every information ready where I know that X other entries than these are obviously 0. So my future programming for any operation are implied knowing they are zeros, and accordingly, I can make my program or logic based on that. Now, having said that, let's see what I can really do with this. For example, I say matrix addition. So I will say except non-zero entries, values are 0. So accordingly, I can make my logic to add 2 matrices, and then wherever non-zero entries are there, and if their row and column are equal, only then the values to be added. Otherwise, these values to be copied as it is. More or less very similar to what polynomial addition we have done. But when you are doing matrix addition, you have one more requirement. Not all matrices can be added with each other. They have to be compatible in the order. So compatibility has to be checked. That means their order must be same. But have we stored the order anywhere? In the new representation, we have not stored the order of the matrix. Maybe you can take extra variables to store the order, or what we can do is now I can have one extra row at the top. So I will say row number 0 will store the total number of matrix rows and a total number of columns, and others will have the values, say 0, 1, and value was 3. So this was, sorry, 0, 3, and value was 3. Then we had 1, 4, and 1, 1, and 4. Then we had 1, 2, and 5. So from this onwards, I will say in my this structure, array of structures, my row 0 will have the properties of the matrix, and because here I have 3 different fields, so I can say first field which I'm using for the word row, maybe I can assume that they are partially like this. So for each entry in row 0, it tells 4 into 5. And for others, it tells the row number and column number for the non-zero value. So from 1 onwards up to 6, non-zero entry details and their positions are stored. And in the row first, in the row 0, I will say I have the matrix properties. This space is available. I can safely use this space to maintain the count of non-zero entries that will indirectly help me to knowing how many further rows are there. So by doing this, now I have, when I said that I have original matrix as a 50, it allows me 0th row to store properties, and from 1 to 49 I can have maximum 49 non-zero entries, or maximum 49 non-zero values can be stored into this. So if I have declared like this, I can definitely say the corresponding values are stored here in this. All corresponding column number for each value are stored, and this becoming a special information within the same triplet, I can use this for stored within the corresponding array of structures. So I need not maintain separate global variables or other variables. Within the 0th row, I'm able to store that. So this way, if the matrices were very big, sparse matrices are only useful when original matrix was very big, and I'm able to save a lot of space. Because if I have, let's say, 4 into 5, only 20 values, out of this, 6 values are non-zero. So 6 into 3, 18 integers needed to store as a sparse matrix storage. But so I'm not gaining much. Earlier I was storing 20 integers. Now I'm storing 18 integers. I don't gain much. If I talk about control information separately, still I am not counting the control information, and 18 information here and 20 here. Not much more. But imagine this matrix was 400 into 500 or 4000 into 5000. And this side non-zero entries were, let's say, 60, and this side non-zero entries were 600. Still, I will be saving a lot of time and space through this. So primarily, we are willing to have that to be handled. Having said that, now let's go further. So my storage becomes much more useful. Storage is defined, and I have a new storage and much more efficient. But once I have done this, of course, now I have to look at the operations. Operations mean what? Operation mean what are we going to do on this? So today our focus is to find transpose of a sparse matrix. Of course, addition and later maybe multiplication can also be targeted. But yeah, transpose and addition are very commonly used for sparse matrices in various engineering applications. So that will be our focus. I want original matrix to be transposed to generate a new transpose matrix. And because it is sparse, so my obviously the transposed matrix will also be sparse. So I want a new matrix to be generated from the original matrix. If we had a normal matrix, means we didn't store it with a new representation, we have stored it with a traditional representation. The standard logic for the transpose, you are well aware. I'm sure all of you have done programming for the original matrix. You have done for I equal to 0, I less than rho, and I plus plus. Similarly, within that, you have written for j equal to 0, j less than column, j plus plus. And what you have done, if you wanted a new matrix to be storing the transpose, you have original matrix and a transpose generated. How? Maybe you wrote here ji, and this side was ij. Primarily this. So this is a simple logic with the initial or your traditional storage. Traditional representation. But if I say, let's say this matrix was of 4000 into 5000 size, then how many times this operation will be done? This step will be executed primarily 4000 into 5000 times. That will becomes very, very big operation. Ideally, out of this, if I assume only 600 entries were non-zero, so probably only 600 values transpose was meaningful, rest all was implied as zero. Then I should probably think of improving this in terms of a 600. So steps could be something like, say, 600 or 1200 or 1800, like this probably. Why I should unnecessarily go for these many steps? I'm wasting. So storage also I was wasting. And once I have improved the storage, I have to think of better logics where I can save this time. So with the traditional representation, storage was also wasted, time was also wasted. So this was effectively time needed, or in general words, I will say time complexity is what is something similarly defined. Of course, for the time being, we will not formally define a time complexity or go in more detail at present. In algorithm subject, you will study this time complexity in much more detail, and that will be the always main focus. In DS, we will slowly discuss about time complexity without formally defining this word, but less focus will be on this. And for the time being, I will not even define and use this terminology. Once you become more programming comfortable, then we will touch upon these aspects later. But primarily, it means nothing but how many steps are executed, basic steps to do that work. And of course, if we can improve the steps, that will be useful. So I have already said that extra loops and extra control statements are never desirable. One reason for that was extra loops will add so many extra steps. Extra statements just add few 5, 7, 10 steps, doesn't make money loss. So having said that, I now already know that my traditional matrices storage and operations both are not suitable for sparse matrix. Storage and operations, they are not suitable for sparse matrix. And I can make better and easier storage, efficient storage, as well as efficient operations. For example, I want a transpose. Well, transpose, you could easily think that it could be simply done nothing but whatever data I had, I could probably interchange these two values. The row and column values were there. My previous storage was 4, 5, 6 here. That was row 0 of the original matrix. So this is my row number. I will say this was my column number, and this is my value in my original matrix. And the values which I had stored was 0, 3, 3, 1, 1, 4, 1, 2, 5. And let me just see the previous entries. 1, 4, 6, 3, 1, 3, and 3, 3, 3, 1 minus 3, and 3, 3 minus 7. 1, 2, 3, 4, 5, 6. Just to show you that we are using exactly the same what we have already done. This is the initial matrix and this was the original storage, but this is the new storage based data. So I'm just showing you the same value here. And of course, initial row is there. So I say this was my original matrix. How my transpose could have been generated? I say the order of the transpose matrix will also remain, the storage requirement will remain still same. This will be index 0 and index 1 to 6. The total entries are always 6. They were earlier 6, so they will be still 6 only. 2, 3, 4, 5, and 6. And what to do? Effectively, transpose means these two values interchanged. So things can be simple by just repeating 6 times and interchanging these values. Probably I could say this will become 303, 114, 215, 416, 31 minus 3, 33 minus 7. 33 minus 4. Sorry, this was minus 4. Yeah, original value is minus 4. So, and here also this order will change. This will become 5. This will become 4. You can note this, that because order will also change and total number of non-zero entries will still remain 6. So this value can be as it is generated. So from here, I can generate the new values, and all others by swapping row and column, I can generate the same values. Probably I can say it will be much more faster transpose, and my steps, if there are 600 non-zero entries for a very big matrix, I will need only 600 steps roughly, and I can definitely save a lot of time. But I say this representation is not the ideal representation. So this is a transpose new matrix which has been generated, but I say some problems are there. Some problems in the representation of the sparse matrix or the transposed matrix. What are the problems? I say the problems which didn't exist in the original matrix, but in the transposed one, those problems have come. Probably you can't understand. So I'll just say, I'll give you a hint that traditional working or users conventional working has a particular way of ordering. Anything we store for the matrix, it is some traditional ordering of the information stored. That ordering was followed into original matrix, but not getting followed, or will, by this process, it will not get followed into transposed matrix. Now, having said that, I will say think over this. Those who are looking at video and want to give it a try, give a pause on this video and think what I have written, and can you understand what is the problem. Of course, once you know the problem, then you will solve the problem. So I will just give a pause here, and those who want, they can pause the video and see, then I will give an answer. So let me now resume. The problem is actually we always store matrix, normally mathematically also, and in programming also, we said row wise. And within row, of course, column wise. So my all data which we store, we have order row wise storage habit. Whatever we do, all operations we do row wise. So that means 0 to 4 or 0 to 3 in this order. And actually in my original matrix also, that ordering was there. Directly or indirectly or unknowingly, I ensured that all entries, non-zero entries corresponding to row 0 were stored here. All entries corresponding to row 1 are here. all entries corresponding to row 2 will be followed by that row 3, then row 4. They are in increasing order of the row numbers because that's the way we normally work. I can't have any entry of, let's say, row 2 here because this is where I stored. See, if you see the previous representation, we started doing like that. All non-zero values from row 0 stored here. All values from row 1 stored next. All values from row 2 stored next. All values from row 3 stored next. So this is how we store. And we always say conventional, meaning user's representation is not to be disturbed. Rest all programmer has to take care. So my original array, this matrix 50 ordering was okay. Not only that, if you see within row, automatically within same row, the values were ordered based on column number. And that's also quite logical. We are doing like that, but primarily we always followed that. Is ordering okay in the transposed matrix? Just have a look. Now, this is row number 3, comes before row number 1, then comes row 4, then again comes row 3, row 3. So this ordering has become a problem. And ordering obviously was going to become problem because previous column number has been swapped and that became the row number. Those who couldn't understand that why did we interchange this value, you could easily see that if I have the original matrix like this, well, what will be the corresponding transpose for the original matrix? If I say this was my original matrix, my transpose should be 0, 0, 0, 3, 0. First row becomes a column 0, 4, 5, 0, 6. 0, 0, 0, 0, 0. Then coming to the last row, 0, -3, 0, -4, 0. This will become 5 into 4 matrix after transpose. Had I planned to store this matrix as a sparse, my focus must have been to store value 4 first, then -3, then 5, then 3, then -4, then 6. Of course, 6 values. Of course, this 6 values, but ordering should have been this. And obviously, this must have been in order of row. Now, if you see carefully, value 3, this is 0, 1, 2, 3. Row 3, column 0. So this entry is nothing but 303. Earlier, this entry was 033. 033 became 303. Similarly, if I talk of some more value, maybe I'll say, let's talk of value 6. 6 value is now entry 4, 1. So I will have this as 4, 1, 6. Earlier, this value was 146. 1 and 4 interchanged. Now this will become 416. So that's why I had the corresponding sparse matrix entry, and they should be in the transposed. Transposed entries will have row and column number interchanged. But the values should be order of 4 minus 3, 5, 3 minus 4, 6. What we generated has been by this order, the values are different. Now you can easily see, ideally what I needed is this should be the better order, but what I am getting is, or I'll say what I am getting is this order. So 3, 4, 5, 6 minus 3 minus 4. Here I need 4 minus 3, 5, 3 minus 4 minus 6. And the reason is simple. I have already seen this ordering is not, this is okay, but this is also okay. Then this becomes violated, this becomes violated, this violated. How to solve this? So now we have to think of a solution. So solution is simple. Maybe you can think of some logic that storage should be manipulated in a way that I should not just swap and store. Maybe you can think of doing some sorting once transpose is generated. That can be one way of thinking, could be one particular logic. We will see whether that is useful or we can make better logic. Of course, we would like to make it faster. If 600 entries are there, sorting means we will have a nesting of the loop 600 into 600 times, because we will have normally 2 loops. So that also will become long number of steps. Maybe still it will work. Can we think of better logic? So I say sorting might not be the only solution. I can think of a better solution. What I say is, effectively what my problem has been that I should be actually storing the transpose also, transpose entries, not just by swapping, in order of new row number. And actually this is column number in original matrix. That means I should not just save the value with the swapping. I should arrange the values based on the old column number, which will become in the new matrix row number. It will be more clear once I reuse that and give an example, and now we will understand this. I say, this is my original matrix. I'll say ORG. Here I have some entries, 4, 5, 6, etc. I'm more willing to focus on entries 1 to 6. In the 1 to 6, what values I had? 0, 3, and 3, 1, 1, and 4, 1, 2, and 5, 1, 4, and 6, 3, 1, and minus 3, and finally 3, 3, and minus 4. Now I say my logic can be that in the final matrix or in the transposed, which value I need first of all. This we will talk later, but I don't need this entry to be at the first place. Which entry I need? I need actually value 4. Why 4? Because that is corresponding to the best possible new row number. So ideally what I should do is, this is the column number in the original matrix. This will become the row number in the new matrix. Same column number will become the new matrix. So I say, first of all, out of all these entries, I should search for column number 0. This column number 0, if it has any entry, that should be, I will be. So that column number 0, earlier that was column, now that will become row. So if there is any entry into the original matrix column 0, which ultimately will become row 0 here, if there was any entry, I will search for that. So I'll go one by one, compare each entry's old column number, which will become new entry's row number. If it is 0, No, means nothing to be done. Then look for column number 1. There is one entry, column number 1. I say this should be stored with the swapped values. This will be swapped definitely. So this is already swapped, but I will store it at some index, let's say k. So k will be obviously 1 onwards because 0th entry is reserved and first entry done. Then any more entry? Yes. Then this should be stored. 1, 3, minus 3. This will come here. Then 1 over, go for 2. Again start this entry. 2, 1. So these values interchanged. Value 5. 2 over. Then what next? 3. This entry. In this order only I will take. Why in this order? They are automatically ordered within the same new row number or old column number. They are relatively ordered with this itself. So column number 3, which will become now row number 3, 3 has entry 3, 0, 3. 3 has another entry 3, 3, 4. But I say this relative ordering was also to be ensured in the sparsed or transposed matrix, and that is guaranteed because for column number 3, the initial row number was guaranteedly before the next entry for available this. For row number 3, there were two values. One had initially row 0, other has initially row 3. They will become column numbers now. I can see I am talking of column number 3, which has become row number 3 into the transpose. In 3, I have entries 3 and minus 4. I must ensure 3 should be stored before minus 4. And in the original matrix also, it was guaranteed that this was stored before for the same column number because they were ordered automatically that way. So knowing that, I can say now this is also automatically guaranteed. Column number 3 over. Then I should see for column number 4. Then I should say, okay, column number 4, 1. So this value interchanged, 4, 1, minus 3. And in fact, this will not stop just here. So I will say now my values are effectively 4, 1, and sorry, this value is 6. So now you can easily see that I am able to get the order which I wanted. Correct order is ensured. So that is what is the logic. Of course, after 4 also I will not stop. If fifth column number existed, then I should check for fifth column number also. They may have entry, they may not have. Sixth column also, if existed, I must have checked that also. So I can't say just to stop at 4. I have to store, if my initial matrix was 400 into 500, column numbers were 0 to 499. So I will go up to 499th column because I don't know which one is empty, which one is not. But having understood this becomes my logic straight away. So now I will say, having known this, I will again ask you to try to write a code of your own. Might not be able to write complete code, but give it a try. Give a pause to the video and start writing of your own some logic. Logic, I mean, you should be able to write the transpose. Transpose operation to be done as a module. So if it is a module, decide what parameters should be, what should be the return type, and code to be written here. Give a pause here and try that. Once you have done that, you can come back again, resume your video and do that. I'm giving a few seconds of pause and then I will explain what logic you should have made. So Let me explain, but I'm expecting that you have already attempted and written something while developing the coding. You found certain problems. You couldn't think something, how to do this or how to find which loop to be applied, etc. So that will help you now once I explain. So what I'm going to explain is here. First of all, parameters, input and output parameters. For doing this, what inputs transpose function needs? It needs the original matrix. So I will say I need SP term original 50. The order of the matrix is also already stored inside, so I need not bother and store explicitly. That is also need to be passed, but it is available in the row number 0 of original. Similarly, I need the second matrix as output to be generated. So I could say SP term trans P to be also passed as a matrix of size 50. And automatically the order total number of zeros, rows, column will also get into its row 0. So this can be safely void. This is how I will decide how to make it as a module. So once this, now I have to write a logic. First of all, how to start? Can I define for row 0 of the transpose? That is straight away definable. So I can write that logic to start with. I will say trans P 0 dot row. Can you tell what it should be? Simple. It has to be original 0 dot column. If earlier my order was 400 into 500, now the order will be 500 into 400. So similarly, this 0 dot column to be this dot row, and total number of values will definitely remain same. So this can be dot val. First row gets defined. Now what next? What logic I said? We discussed that we are going to compare this value initially with value 0, next with value 1. We said we will start comparing this value onwards. What is this index? This is original matrix at some index. Initially index is 1, index 2, and so and so. So this index is 1 onwards up to something. Dot column, I compared it with initially 0, then 1, and if there are total 499 columns, I said one by one I will compare. So I wanted something like if to be applied. If to be applied, what should I write here? Of course, some index. Index to start 1 onwards, then later 2, later 3, up to what? Up to 6. What is 6? This count. So I can say I need, let's say, some variable n, which I can say original 0 dot val. N is the total number of counts, so I can take extra variable. So I took extra variable. So I need this to go up to n. What is my logic? I said this column number to be compared with 0 for all entries. First time with 0. Original 1 dot column, then original 2 dot column, original 3 dot column, original 6 dot column. All values to be compared. This means there should be a loop immediately outside, and let's use this as a j. So now I will say for j equal to something, j less than equal to something, j plus plus, and what I require is if original j dot column, because that old column number will become new row number, equal to initially 0, then I have to actually store it into my sparse matrix or transpose matrix. So I will say in transpose somewhere dot row will be stored equal to original matrix column. Similarly, dot column to be stored, similarly dot value to be stored. Now, in a transpose, first of all, what it should be, I want a j to start from 1, go up to 6. So 1 to n. Now, what should be original? This, if the matching happened, this entry was stored, this full entry from original j. That means original j dot column, original j dot row, original j dot val. Where to store in transpose? First time at index 1, next time at index 2. I don't know how many entries will come, so I can't say this will be exactly j. This will be exactly something similar to j or relevant to j. No. One j could be firstly initially 1, later an entry for j will come maybe at 6, maybe at 20. So I will say I can take a separate variable k, and I can definitely make k to start with 1. And of course, once done, k plus plus. So this, if the condition is true, effectively I'm generating the element, and this loop to be continued. For checking all entries corresponding to old column number 0, which in the transpose will become row number. Next time what? This 0 should be 1. Next time this should be 2. In general, I will say let it be I. So now I need I to change for every 4 of j. So I loop will be outside, I equal to something, I less than or less than equal to something, I plus plus. But I should be an outer loop, j should be inner loop, because once I is taken as 0, all entries of original should be taken. For one I, all j should be tried. So nesting is decided like this. I want same I to be used for all different original entries. Then same next I to be tried for all entries. Initially, I is 0. I am looking for all entries for old column number 0. Once they are exhausted, again start. Take I as 1 and again check for all entries which are relevant or belonging to column number 1. Original column will become now row number. So column number 1 in the original. So from where I should start? Initially, my column number can be 0, and I should try for all possible columns. How many columns? Total 499 up to 0 to 499. Means effectively this is nothing but original 0 dot column. This tells the size of the initial columns in the original matrix. Those many times to be repeated, and I should do this. I think this much explanation is simple and sufficient for you to try. Just for convenience of yours, I will write my transpose function and inner logic with more clarity so that you can think of doing now. So my row 0 of sparse or transpose. So I will say this is my transpose function full. So name of the function and name of the variable should not match. So I will say let it be sparse transpose. So transp matrix row 0 to be generated with all entries. Then I will say let k be equal to 1, n be equal to defined, and I need a for loop I equal to 0, I less than something, I plus plus. Within I need a loop for j equal to 1, j less than equal to something, j plus plus, and then if I put braces no harm, I need here if original J dot column to be compared with something, and then storage to be done. And then, of course, after storage, K++ to be done. So having said that, this will become a logic, and this is what I am supposed to implement in this particular way. So now homework for today. Implement, of course, transpose of sparse matrix. So this module to be written. Of course, that is a homework for all. But how will you verify whether you generated a correct transpose or not? So you should be able to write main, etc. also. So if you write main, you have to read a matrix also. A sparse matrix to be read, transpose to be found, and of course to be accordingly displayed. So now I say additional optional practice problems I am telling you. Those who want to try, those who are good programmers, they can think of doing this also. And they should try to implement. How will you do the reading? So reading can be in two ways. One simple way can be read the sparse representation based storage itself. That means effectively you will store it by reading for every matrix, original matrix, the way we had already stored. Read that way. So you need not generate. But I will say, can you think of doing it? That read a traditional matrix fully. So 4 into 5 matrix means you will read 4 into 5 matrix the way you were reading. And store actually in to the sparse representation. So your reading will be done in the normal matrix manner. Like you will say, enter for full row, first row. So you will give a 0, 0, 0, 3, 0, like this. Then you will say enter for second row, 0, 0, 0, 0, 0, 0. Then you will say enter third row. Then you will say 0, 4, 5, 0, 6, like this. But storage will be actually done, and you will have it as 1, 2, 3 entries. Row number, column number, and value. So this can be one of the way of doing this. So that can be extra module through with this. Similarly, display. How will you display your output? One way can be display the transposed sparse representation. Directly, whatever you have generated, the SP term array sparse term and the transp matrix generated, same transp you can display by writing 0, 1 or dot row, dot column, dot val to be displayed. And 0th row also displayed, first row also displayed, and up to n or up to count all rows displayed. Second, display it like a traditional matrix with zeros also. Wherever entries are non-zero, those are shown as non-zero, and all remaining entries are also shown at possible places. That will mean, say, you will display it 5 into 4 matrix, saying that my output generated is nothing but 0, 0, 0, 0, 0. 0, I have already probably somewhere stored. Let me just check there and then show you. So I'll say, yeah, this was 0, 0, 0, 4 zeros, and then 0, 4, 0, 3, 0, 5, 0, 0, 3, 0, 0, minus 4, and 0, 6, 0, 0. So this output is displayed, but it was never stored. So this display is generated via a module which is receiving the sparse data and sparse matrix representation, and from there, while displaying, it displays 0 wherever needed. So my input supplied was 0, 0, 0, 3, 0, 0, 4, 5, 0, 6, and so and so. So this could be traditional input supplied, and this could be the traditional output. But internally, everything is sparse storage only. Only sparse storage. No other matrix stored at all. Only for the reading or writing purposes, you are having additional printf, scanf, etc., and rest everything this. So this can be one additional homework. So I say just now giving you an overview of what homework I have given. Transpose to be computed for everyone, and an optional homework or optional practice. Read and display improved using traditional representation also. That is one thing. Secondly, I say my sparse matrix or sparse representation can be done using 2D array also. Why to have a structure? What does that mean? Effectively, this original matrix which I generated can be treated to have dimensions for the column only 3, 0, 1, 2, and this side I can have 0 to 49. So I can say this will be nothing but int original 50 into 3, where any original I dot row which was earlier used, it is equivalent to now original I 0. Similarly, dot column is nothing but original I's column number 1, and dot val is equal to nothing but original I2. That's it. So instead of having a structure, I can also use this. So implement full program for transpose of a sparse matrix using 2D array representation. 2D array doesn't mean full row into matrix, 2D array of sparse storage instead of a structure. That's it. So with this, I will stop. I again say this is optional. Those who find it difficult or those who are not doing good programming at present, they need not bother about this, but others can try. All the best to all of you. Bye-bye. Have a good day. Enjoy.